Now I want to talk about t-tests. But first, let's talk a little bit about why we need them. Again, we're just going to go back over. What's actually going on is when we were talking about confidence intervals earlier, we didn't know the true mean necessarily, but we did know whatever our x bar was. So we could actually make our calculations without knowing the true mean, but guessing at it, just because if we had swapped places between the two of these, it would have actually had the same result. Now, we were making a presumption that we knew what sigma was. Most of the time, we can know that for small numbers. I mean, we may be able to figure that out a priori. If we take large numbers of samples, naturally we can calculate what the standard deviation is, and then from that, if we want to calculate the standard deviations of the means, we can just take sigma over the square root of n, and if we have a large enough sample, we can use s over the square root of n, and that's a pretty good approximation. When I say large enough sample, basically that means the sample size n is greater than or equal to about 40. There's one situation, however, that we have not covered, and that is where we have small numbers in our sample and we don't know a priori what the standard deviation is. Well, what do we do now? We use the t-test, exclamation point. Now we're going to have our t-test magically appear here, so it is before us. And let's say that I wanted to read a t-distribution is pretty much like a Gaussian curve, but it's kind of got broader tails to it. And the way you read them is, of course, a little different, just to make things more difficult for you. So here we go. Let's say, see this alpha right here? The alpha is that area. So these are called percentage points. So here are the areas. You notice it's really quite different than the way we were reading for the Gaussian curve. Let's say that we have an area under there of 0.05. So we're going to grab that. And we want to see, now before we would have said our z-score, but now we're on a t-distribution, so we need what's the t-score if alpha is equal to 0.05. The way we do that is just, okay, we're at 0.05. Now we have to know how many degrees of freedom we have. So in a case where we've got 10 degrees of freedom, we would, so we're looking over here, we've got 10 degrees of freedom, 1.182. So the t-score for 5% greater than that value is going to be 1.812. And we can say then that the probability that t with 10 degrees of freedom is greater than this value, 0.05 and 10, is equal to the probability t10 is 1.812, and that's equal to 0.05. Now also keep in mind that if you have a t-score here, then actually it is related to the t-score on the other side, because remember, this other side, if you had a t-score, whatever that t-score is right there, it will give you all of this area, right? And so that's actually all of that area is equal to 1 minus alpha, right, as opposed to alpha right there. So because of that, we can say this t-score on the other side is actually equal to t of 1 minus alpha with that number of degrees of freedom and that's equal to minus t alpha n. So in other words, this t-score is related to this t-score through these equations. Now, the nice thing about t-scores, though, is that we can use them pretty much exactly like z-scores. So just as before we had calculated, we laid out our edge limits for z-scores for confidence intervals, we can do the same thing for t-scores. So we'll say the probability of whatever our particular sample mean minus t-score alpha over 2 and minus 1, and whatever that sample, because we're going to calculate for a small sample, n, less than or equal to mean, less than or equal to x bar, plus t alpha over 2 n minus 1, that's our number of degrees of freedom, times s or the square root of n. All of that is equal to 1 minus alpha. And then we can define our 100 times 1 minus alpha percent confidence interval on mu is going to be just x bar minus t alpha over 2 n minus 1 s over square root of n, and less than or equal to mu, and that's less than or equal to x plus t alpha over 2 n minus 1 s over square root of n. And this value right there is, well, I should actually extend that over to here. That is the lower 100 alpha over 2 percentage point. So I'm going to write this down. This is the lower 100 alpha over 2 percentage point of the t distribution with n minus 1 degrees of freedom. So now we can move on to solving some problems. So now let's look at a problem that in which we're required to determine the t percentile required to construct two-sided confidence. So this is two-sided confidence levels of 95% with 12 degrees of freedom. Now, so that's the first one we want to do. So a confidence level of 95%. 95 would mean we're trying to build something, and remember it's two-sided, that its quad level is 5% essentially. So that means, because it's two-sided, it's going to be 0.025 here. So we go down, boom, there we go, there's 0.025, and then we want to see what that t value is. Well, they tell us it's 12 degrees of freedom, so it's got to be right here. Now remember, it says 12 degrees of freedom, which means actually n is equal to 13. So this should be t of 0.025 with 12 degrees of freedom should be 2.179. Okay, so hopefully you could see that earlier. So anyway, we've got t is equal to 0.025 and 12. Now let's go to the second one, which is a confidence level of 99.9 with 15 degrees of freedom. So 99.9 means that the alpha's got to be 0.001, which means alpha over 2 is 0.0005. Well, let's go see if we can find that. Aha! It's right down here. So we've got this, and we said 15 degrees of freedom, so we're going to go look over here, 4.073. So now we know that T of 0.0005, 15 is going to be 4.073. And hopefully, there, now you can see it better. Okay, now let's say that I wanted to do, instead of two-sided, that I was going to do one-sided. I'm going to do the same thing but as here, but it's going to be one-sided now. I'm trying to find my t value, then t, let's see, of 95%, so that means it's going to be 0.05 is our alpha, and we don't have to divide it in two. So now we can just go directly to 0.05, and let's see, we had 12 degrees of freedom, so now we can find this as T of 0.05 with 12 degrees of freedom is 1.782. And likewise, right here, if we wanted to go to 99.9 with 15 degrees of freedom, well, we don't have to cut it in half anymore. So we're at 37, so that would be T of 0.001, and 15 degrees of freedom is 3.733. So that all makes good sense. Now let's work problem 8-26. And in this problem, you're given a random sample that's been taken from a normal distribution, and the software package gives you the following information. It's a spurious software package, so it only gives you some of what you need. Well, this is standard deviation, but we'll cross that out and just go like this. So the variable itself is x. We don't know how many were in the sample. We don't know the mean. We don't know the standard deviation, the variance. We don't even know the standard deviation of, well, we do know the standard deviation, but we don't know the standard deviation of the means. But we do know the sum that we got. So they're asking us to, first off, please figure out what some of those missing variables are. So we know right from the get-go that for our standard deviation of the sample means, we're just going to calculate this number. And since we already have sigma, and we've got this number, so we can quickly calculate what the number is. Going to be 6.11 over the square root of n is going to be 1.58. So therefore, we're going to have n is equal to 15. Now the mean is just going to be equal to the sum over n. So that's 751.4 over 15. And that's equal to 50.0933. And the variance is just sigma squared, and that's 6.11 squared, which is 37.3321. Now, let's say that we wanted to find the 95% confidence interval on the mean. So we've got n is equal to 15. X bar is, well, we've got that right from up here, 50.0933. S is equal to 6.11. And now what we're looking for is T of 0.025, because we're cutting it, we're looking for a two-sided confidence interval with a number of degrees of freedom. Be careful here, it is n minus 1, so it'll be 14. if we go down and look, let's go look at 0.025. Here we go, 0.025, and we need 14 degrees of freedom. So there we go, 14 degrees of freedom, and we're at right here. Okay, 2.145. So there we are, we're at 2.1045. So this number is 2.145. And now we can say that x minus t of 0.025, 14 s over square root of n is less than or equal to mu is less than or equal to x bar plus t 0.025, 14 s over square root of n. And now plugging in actual numbers, so we shall plug in green. We'll say that we've got 50.0933 minus 2.145, 6.11 over square root of 15. It's less than or equal to mu. It's less than or equal to 50.0933 plus 2.145, 611 or 6.11 over square root of 15, and that simplifies down to 46.709 is less than or equal to mu is less than or equal to 53.477, and that is our 95% confidence interval. Now let's move to problem 828. And here we have an IZOD impact test was performed on 20 specimens of PVC pipe. The sample mean, oops, that's the sample mean, so it's got a bar above it, is 1.25, and the sample standard deviation is S is equal to 0.25. Find a 99% lower confidence bound on the impact strength. So we would begin by saying, what's our N? Well, it's 20, X bar is equal to 1.25, S is equal to 0.25. So we're just calculating what we know. Let's see now, 99% lower confidence bound. So we're actually looking for T of 0.01, and we don't have to cut it in half because it's only single-sided. And our degrees of freedom are 19. So if you go down, let's go look at 0.01 and 19. So we're looking at 0.01 with 19 degrees of freedom, 19, and we should have 2.539. So we'll go back up here, and we'll say that this is actually 2.539. Now we can say that X bar minus T of 0.01, oops, 1 and 19, and we'll put our S and square root of n. It's got to be less than or equal to mu, and that means 1.25 minus 2.539, 0.25 divided by the square root of 20, and that should all be less than or equal to mu. If you calculate out that number, it should be 1.108 is less than or equal to mu, and that is our 99% lower confidence bound on mean IZOD impact strength. Ta-da!
Welcome to Eyewitness News at 6 with Susan Ortega, Evan Baxter, Fred Donahue, Sports, Dallas Coleman, Weather, and now, Buffalo's #1 news team.
Good evening and welcome to Eyewitness News at 6. I'm Susan Ortega.
And I'm Evan Baxter, and here's what's making news. A potential scandal with the Buffalo PD surfaced today when the mayor demanded that the chief of police as a response to allegations. Sorry, I seem to have something stuck in my eye.
Somebody get him some water, please.
It looks like my new co-anchor may need a glass of water.
Oh. Do caca poo poo. Sing the pee pee.